Hello, Inforce. I'm excited to get started. My name's Andrew Hopkins. I'm a senior software development engineer working on AWS's open source cryptographic libraries and tools. Today, I'm excited to introduce AWS-LC, briefly reintroduce S2N TLS for anyone not familiar with it, and discuss how we migrated S2N TLS to use AWS-LC. Along the way, I'm going to cover what we improved in AWS-LC and how you can get started using it yourself. Quickly, show of hands, who here is familiar with using libcrypto or is familiar with cryptographic toolkits? Oh, seems like maybe a little bit less than half. Don't worry, I'll get everyone up to speed pretty quickly. I'm sure everyone here is very familiar with using AWS services. You might be familiar with like CloudFront, Amazon S3. These services are available over the internet, and what they have in common with other tools such as the AWS SDKs is they need a mechanism to communicate over the internet, and they need a mechanism to do so with privacy and security in mind. The way these higher level services and applications accomplish this is by using some network security protocols. Everyone here has probably used TLS, the transport layer security. This is how you probably are most familiar with connecting to AWS services. TLS is a protocol. It defines the message format and handles the negotiation of which algorithms and keys are used to secure your communication when connecting to AWS. Another protocol you might be familiar with is SSH. This is how you will be connecting to your Linux-based EC2 instances. And like TLS, it defines the message format and handles the negotiation of algorithms. But critically, these networking security protocols don't actually implement any of the algorithms. They rely on another dependency to actually provide those implementations. And that's where cryptographic toolkits come into play. Cryptographic toolkits will provide both the algorithms and some of the utility functions you might need in your higher level protocols and applications. You might be familiar with X509 certificate parsing and validation. This is how AWS services authenticate themselves to you as the customer to make sure you're connecting to the real AWS services. Inside these toolkits, you will also find the algorithm implementations. I'll be talking a lot in this talk about elliptic curve Diffie-Hellman. This is commonly used in TLS and SSH to establish secure keys between the clients and servers. Another algorithm you'll hear me talk a lot about today is AES-GCM. This uses the secure keys from elliptic curve Diffie-Hellman to secure your data in transit to AWS. Every cryptographic toolkit will also possibly provide optimizations that depend on specific processors. This is where you have hardware instructions to do crypto faster. And this is the lowest layer here that's kind of processor specific. Every cryptographic toolkit will have a choice of which algorithms to provide and which APIs to provide. And for AWS-LC, we made a particular choice. I won't cover too much of all of the algorithms or functions we have. For that, I'll refer you to our open source documentation and public header files. But what's important for AWS-LC is we chose our particular API trying to target the most important functions and algorithms for AWS and our customers. And another key component of AWS-LC is the FIPS module. Don't worry, I'll cover more about what is FIPS later on, but for now, just remember that we validated a subset of AWS-LC, and that is the FIPS module. Every team at Amazon has tenets, and AWS-LC's team is no different. First and foremost is correctness and security. We designed and implemented AWS-LC with correctness in mind. This is ensuring we get the correct and expected answer for all the algorithms you are using. But it's not just sufficient to be correct, we also must be secure. This is secure from potential side channel attacks, where you reveal sensitive information, and also from memory corruption, where maybe we reveal information in memory that you don't expect. We use a variety of tools and tests to ensure AWS-LC is both correct and secure. Next, most important for us is maintaining backward compatibility. We realize AWS-LC is constantly in motion. We're developing new performance enhancements, new security features, and for our customers and AWS teams to easily adopt those new features, we must make it easy for them to stay up to date. And we do that by maintaining backward compatibility such that we're not breaking customers or other dependencies every build. And like I mentioned, performance is key for Amazon. We are super focused on performance as well for AWS-LC, but critically, it's not performance at the cost of security, and we're trying to not hurt security in the aims of performance. We're aiming to provide both high quality, secure implementations and high performance implementations. For some certain workloads, compliance plays a key part with cryptography. This is where FIPS 140 is an example of this, and we want to make sure it's easy for customers who need to meet certain compliance are able to do so by using AWS-LC, and we want to make sure customers that need that compliance can continue to get a good experience, so we're continuously revalidating AWS-LC to make sure you can always use the latest features and enhancements. Finally, AWS-LC is developed open source on GitHub. We believe it's important for us to be transparent, and this also helps it be easier for our customers to interact with us and for us to interact with the broader open source cryptographic community. And by being open source, we're able to contribute back some of the valuable lessons learned and improvements we've made. For anyone not familiar with S2N, it is a family of open source cryptographic protocol libraries focused on encryption in transit. The two key libraries that we'll be talking about are S2N TLS and S2N Quick. For anyone who might have seen my coworker's presentation, NIS 304, using S2N Quick, they went into more details about the advantages of Quick. But for this talk, we'll be focusing on S2N TLS, which, like the name suggests, is a library that implements the TLS protocol. And if you remember from the previous slide, S2N TLS and S2N Quick are protocol libraries, and they need another library to actually provide those algorithm implementations. Currently, S2N TLS supports multiple cryptographic toolkits. We do this to maintain it, to make it easy to use what is available to you in your environment. And this talk is all about the work we did to add support and migrate S2N TLS to AWS-LC's toolkit. For a timeline of the events, S2N TLS launched in 2015 and quickly gained internal adoption, and by 2017 was serving all of Amazon S3's front-end web traffic to customers. After we hit that milestone, we began looking at post-quantum cryptography, and in 2019 we added support for hybrid post-quantum key exchanges. We did this with 3 AWS services to let customers begin experimenting with post-quantum cryptography in AWS. And these hybrid cipher suites maintain the high security and confidence from the past algorithms with the expected post-quantum security of the new algorithms. This is particularly exciting because NIST just announced the final selections for some of the post-quantum cipher suites, or ciphers. With the advancements we were seeing by taking greater control of S2N TLS's algorithm implementations in cryptography, we began investing in our own cryptographic toolkit, and in 2019 we launched AWS-LC with the AWS Nitro Enclave's SDK for C. And shortly after launching, we began the work to migrate S2N TLS to AWS-LC. And along this whole way, we've been working on x86 and ARM optimizations in AWS-LC, particularly looking at newer Graviton instances and taking as maximum advantage of the new performance they offer. And in December of 2021, we submitted AWS-LC for FIPS 140-3 validation. And again, I'll cover more about why that might be important to your use case later. So what was actually involved in that migration of S2N TLS to AWS-LC? We identified 4 key checkpoints. First was coexisting with other dependencies. We knew from the start we only wanted to migrate the TLS layer to using AWS-LC, and we wanted to leave the rest of higher level applications available to use whatever toolkits they wanted to use. This was important for us because it minimized the blast radius by minimizing the change. We were only changing the TLS layer. Next was making sure AWS-LC provided the same APIs that S2 and TLS needed, and that those APIs behaved the same that they expected them to. Like I said, a theme of AWS-LC is performance, and we wanted to make sure by migrating to AWS-LC, we didn't negatively impact any of S2 and TLS's customers' performance. And finally, a key part of all of this was meeting the same regulatory requirements that S2 and TLS needed. So the first step for the migration was making sure AWS-LC could coexist with other dependencies. And to kind of understand the problem, we'll go to quickly explain linking, and in this case, linking on Linux operating systems. Here we have two applications and two libraries, A and B, that each provide two functions, A and B. And here, everything is okay because the libraries are providing different functions, so there's no conflicts, and the application can use both libraries together seamlessly. This is a small problem for AWS-LC, though, because we want to maintain some level of cross-compatibility with existing toolkits. So what this means is AWS-LC provides similar functions with similar names, and in many cases the exact same names, as other toolkits. And with at least native libraries, you're not allowed to have multiple functions with the same names loaded at the same time. This will result in a symbol conflict, and depending on your tool chain and how you are using us, this will result in a link time error or a runtime only one library getting loaded. And this is a problem, again, because we wanted to make it easy for customers to move to AWS-LC and minimize that blast radius so it's only S2 and TLS using us. Our solution to this was introducing a prefix static build into S2 and TLS. Using this technique, we're able to build AWS-LC and S2 and TLS together, and then update all of the symbols and the symbol references in those two libraries to use a prefix so they don't conflict with other libraries in use on the system. This is extra valuable for S2 and TLS because they can then bundle us inside their library as a static artifact and be completely transparent to customers about what cryptographic toolkit they're using. And this lets S2 and TLS move their customers onto us seamlessly. So the next checkpoint for us was ensuring API compatibility, and the way we did that was through exhaustive testing. We built our continuous integration using AWS Code Build and AWS Device Farm. Code Build enables us to run multiple test suites all in parallel across multiple operating systems and processors, specifically x86 and ARM. AWS Device Farm lets us do the same, except testing on mobile operating systems and mobile processors. And this ensures no matter where you use AWS-LC, you get the same quality assurances and same compatibility that will build successfully in your environment. The first part I'd like to call out is unit tests. Unit tests are great for testing algorithms that have a standard. These standards will define exactly what the algorithm should do, and in many cases they will include known answer tests, such as for AES encryption, given a particular key and plain text, you will always encrypt and get this ciphertext. And AWS-LC uses this for all of the algorithms that we support. The next interesting part was fuzz tests. Fuzz tests, we use libfuzzer to generate random inputs and pass them to AWS-LC to make sure there's no undefined behavior. But we actually went one step further with differential fuzzing. The differential part of this is we actually test AWS-LC against multiple other cryptographic toolkits, ensuring our library produces the same output as the other toolkits and that everyone agrees on the correct answer. But just with unit tests and fuzz tests, that's actually still not sufficient. We build, as a part of our build, S2 and TLS and ensure their tests pass when built with us. And this actually kind of found a fun, interesting bug early on in development. Like I said, some algorithms have standards, and those standards have known answer tests, but some functions in AWS-LC don't have a standard. In one case, base 16 or hexadecimal encoding of data, there's no standard or agreed upon convention whether you should use capital or lowercase a through f's. And in this case, AWS-LC actually differed from S2N TLS's expectation. But again, because we're running S2N TLS's integration tests with AWS-LC, we're able to catch that and fix it and make sure everyone agrees on the correct capitalization of hexadecimal data. The next interesting box I'd like to dive deeper into is formal verification. Formal verification can be used to mathematically prove properties of a system. And this is very valuable for AWS-LC because it lets us prove exhaustively that our algorithms are correct. These known answer tests that I talked about in the unit tests only prove that we get the correct answer for a certain subset of the inputs. There's no guarantees that there aren't other subtle edge cases or conditions we don't handle. Using formal verification, we're able to prove exhaustively that for all possible inputs, AWS-LC is producing the correct output. And this is valuable for S2N TLS because they're used across many AWS services handling a lot of data and is very likely to possibly hit these edge cases that thankfully formal verification can prove that we're not going to hit. For formal verification, we took two approaches. First, we wanted to formally verify our existing implementations. One example of this is AES-GCM. We have a highly optimized, highly performant version of AES-GCM included in AWS-LC that is built using C code to provide a nice customer API and optimized machine assembly code for x86 and ARM. We didn't want to necessarily have to change this implementation, but we still wanted the benefits of formal verification. That's why we created the AWS-LC verification repository, which includes formal verification proofs of some algorithms in AWS-LC. We built AWS-LC verification using Cryptol, which is a domain-specific language for specifying cryptographic algorithms. This lets you mathematically specify the algorithm once and then reuse that specification in multiple different areas. We did that using the software analysis workbench. What the software analysis workbench does is it proves equivalence, that our C and x86 assembly code is equivalent to the mathematical specification of AES-GCM in this example. And this is powerful because it lets us change our AWS-LC code and prove that it is still correct because the mathematical specification in Cryptol did not change. That is written kind of once and it never has to change, whereas the code can be updated to take advantage of new improvements. For more information on this, you can see the AWS Science paper, Verified Cryptographic Code for Everybody. And I'm excited to talk about the fact that we contracted with Gawa, the developers of the software analysis workbench, and Cryptol to add additional functionality to their public tools that you can also take advantage of. They built two new tools to accomplish all of this, specifically being able to prove and reason about mixed C and x86 assembly at the same time, and the ability to prove unbounded results, or results about unbounded input. Yes, using this technique, we were able to keep our fast, optimized implementation and get all of the high quality assurances that formal verification provides. The next approach we used for formal verification was developing all new code and the proofs in parallel. And that's why we made S2N BigNum. For those who aren't familiar, a BigNum library is useful in cryptography to do mathematical operations on numbers that are larger than what a CPU can traditionally handle. This is convenient and required for some cryptography, such as elliptic curve Diffie-Hellman with 500-bit numbers that don't fit in a traditional CPU register. We knew early on that we wanted to improve our elliptic curve performance because this is used in every single, or not every single, most TLS handshakes use elliptic curve Diffie-Hellman, and it is a key performance for improving the overall handshake latency. So we began by writing optimized assembly code for x86 and ARM, and in parallel with that development, building the proofs that proved the assembly was equivalent to the mathematical operation. You can think of two 500-bit numbers added together will always produce the correct result. And once we had S2 and Bignum fully written and verified, we were able to integrate that code into AWS-LC's elliptic curve functions. And S2 and Bignum is also available as a standalone open source library for those of you that also are working on cryptographic toolkits. This kind of is a nice segue to performance. So we built S2 and Bignum both for the performance benefits of a highly optimized implementation of Bignum libraries, but we also wanted to look at our other performance. And we took a tiered approach to this performance testing. Starting with the bottom layer, AWS-LC, we looked at the cryptographic algorithms in isolation. This is our performance of our code tested using our speed tool that's available for you to also run in our repository. Looking at this, we were able to compare the different parameters and algorithms on different platforms and see how the performance compared and where we wanted to improve things. But that's not the complete picture. This doesn't really show the relative importance of some of those algorithms or how they get used in real applications. For that, we benchmarked S2 and TLS. At the S2 and TLS layer, we're looking at handshakes. This is what customers actually do when they're connecting to AWS for the first time. They're establishing those shared keys, and that is one of the key performances impact for first-time connections. But that's not necessarily most important for all connections. For some AWS services, you might be transferring large amounts of data, and a small little TLS handshake is an insignificant amount of that performance. So for that, we looked at the data encryption. This is the actual bulk encryption of the messages you're sending back and forth to AWS. And this is where benchmarking ASGCM was important. But still, this is not the complete picture. For the complete picture, we had to look even one level higher with applications. At the application layer, we're actually looking at what is the customer impact of this migration to their overall request flow. Very few customers are probably thinking about TLS, but they're thinking about their DynamoDB get item requests and the performance of that first time you're connecting to a new service. And this is where customer request measuring is important. We looked at latency for our customers and CPU utilization for the AWS services that were deploying AWS-LC. And with this, we were able to identify and improve the algorithms. This is why, like I said, we invested in S2 and Bignum, and we also invested in some other algorithms that were most important for AWS and our customers. And I'm excited to share some of the performance results with you. So this table is showing AWS-LC's pure performance tested on an EC2 C7G instance. This is kind of that bottom layer of performance I talked about on the previous slide, and is showing our performance on the same instance with our code from 2020 and today in 2022. I should call out that we were very happy with our performance initially in 2020. We were close matching the industry performance for these algorithms, but we knew with the increased adoption of Graviton and ARM processors that we wanted to invest in further improving that performance for ourselves in AWS and for our customers running their workloads on ARM. So this table shows elliptic curve Diffie-Hellman with 3 different parameters. These different parameters provide different levels of security. P256 is one of the most common ones because it provides an adequate level of security and is the most performant, and is the most widely used ECDH variant. But what I'd like to highlight is P521. For a reference point, a standard TLS handshake within one AWS availability zone is going to be on the order of magnitude of a few milliseconds. So most customers didn't want to use P521 because the performance impact of migrating to that higher level security meant that they would be effectively almost doubling their TLS handshake time. But through the use of S2 and Bignum and other improvements, we were able to get that latency down to almost half a millisecond. And at this level, it is no longer prohibitive to use P521 for applications, and you can take advantage of the higher level security provided by P521. I also included two symmetric ciphers, ASGCM and Cha-Cha-Poly. These are used for the bulk encryption between AWS and clients. Here, it's measured in megabytes per second, and higher values are better. And you can see we were also able to improve the performance of both of these. And ASGCM is highly used because it's been highly optimized, and there's lots of hardware support already in use in modern processors. And Cha-Cha-Poly is widely used because it's efficient for low-powered devices such as phones to implement in software. And I should quickly call out the ECDH numbers are measured in milliseconds. So that is the time for one operation, and lower is better. So we accomplished all of this through a combination of algorithm improvements and taking better advantage of those hardware capabilities to us. And what's really exciting is we're able to share some of these performance improvements with the broader cryptographic toolkit community. So we took the lessons we learned from developing these performance improvements and contributed them back to other open source libraries. We did this because we knew it was important for our customers to have the fastest possible crypto, but not all of our customers are going to be able to use AWS-LC on day one, but they still deserve to have the best performance and cryptography available with whatever application and toolkit they're using. So we're able to contribute some of these changes back, and we're going to continue to contribute future changes when possible. The next checkpoint for the S2N TLS migration was FIPS. Who here is familiar with FIPS 140? Way more people, exciting. Great. So you're probably all familiar with the fact that we're kind of in this transitionary period. We used to have FIPS 140-2. It was published in 2001. And now we're moving to FIPS 140-3, the new standard for cryptographic modules from NIST. And in this transitionary period, NIST added some new requirements to the FIPS 140 standard, and have also kind of tweaked some of the algorithms available in the new standard. And AWS-LC had two main development points that we had to tackle in our submission process for FIPS. The first is randomness. So randomness is very important for cryptography. This is what ensures when you generate your keys that you're generating secure keys that aren't able to be predicted or guessed by an adversary. These randomness also comes into play in TLS that uses random nonces and other random values that can't be predictable. So traditionally, cryptographic toolkits have used hardware sources of randomness. You might be familiar with RD-RAND on x86 processors. This is an instruction that calls special hardware on your processor that returns random values. This is super valuable for toolkits because this is very fast, and it's very efficient to use RD-RAND. However, new in 140-3 is the requirement that cryptographic modules have to meet the NIST Special Publication 800-90B requirements. And this is the requirements for secure randomness generation. And what this basically does is it moves the source of randomness into review for the module. And this is tricky for AWS-LC because we're a software library. If you're developing, say, like a hardware security module, you're going to have one processor and one version of code that you're targeting, and you can go through the review process to make sure that your source of randomness meets this requirement. But AWS-LC is going to be run on a variety of platforms, and we don't necessarily have the capability to review with NIST and our FIPS lab all of those platforms. So we needed another solution to meet the 800-90B requirement. And for this, we used the technique called CPU jitter. CPU jitter provides a method in software to produce secure, high-quality randomness without requiring any specialty hardware on your processor. All it needs is the very common instructions to get accurate timing, and doesn't necessarily require on specialty RD-RAND instructions. So using CPU jitter is valuable for us because they've already been shown to meet the requirements of 800-90B. So we were able to take CPU jitter, which is both a process for generating randomness and is also the name of a library that implements that process, and integrate it into AWS-LC's secure key generation algorithm. But our key generation algorithm also lets us mix in additional randomness, which we're still doing using the traditional hardware random number generators, because those are, like I said, very high performance, very cheap and easy to use. So we get kind of the best of both worlds, the FIPS security from CPU jitter and the performance of the hardware random number generator. The next requirement that was new for 140-3 was the requirement to add a approved service indicator. So if you look back at FIPS 140-2, you might be familiar with reviewing security policies. These are documents that outline what a cryptographic module has been approved to do, and it outlines the algorithms and APIs that are approved. New in 140-3 is the service indicator. This is a runtime method of providing similar information. This requires AWS-LC to have new public APIs that you as our customers can call to see if you're using AWS-LC in an approved manner. And this is valuable because we provide both approved and non-approved algorithms at the same time. This is useful because there are many use cases that don't need FIPS-approved crypto for some of the utility functions, and it's convenient for you to continue to use those from AWS-LC. And using the service indicator, you can now easily check that you're doing the correct thing that you expect. And as the service indicator is a new requirement from 140-3, and we were a new library going through the submission process, we were one of the first to implement a approved service indicator. And again, we were able to share that implementation with other open source cryptographic toolkits, just saving everyone time and helping to standardize on the API that is used for the indicator. So with all of this, we were able to finish the regulatory requirements for S2N TLS, and with that, fully unblocks the S2N TLS migration to AWS-LC. So we had accomplished making sure we were compatible with other dependencies. We ensured we were API compatible with the cryptography that S2N TLS needed. We ensured we met the same performance requirements and regulatory requirements. But that's just the beginning. AWS-LC and S2N TLS are both available for use on GitHub. And on GitHub, you can see more details about how we specifically implemented the service indicator, all of the performance improvements, and how S2N TLS managed the prefixed internal build of AWS-LC. But AWS-LC is also not just useful for AWS. We believe it's useful for you, our customers, client side. And there's actually already some existing ways you can use AWS-LC, such as with the AWS Java SDK. This is the existing Java SDK that you use when connecting to AWS. There's a new version that is built on top of the AWS Common Runtime, which is a lightweight C library that provides common functionality for all of the AWS SDKs. And this is built using S2N TLS and AWS-LC. So by updating your code to the new AWS Java SDK v2, you can take advantage of all of the performance and security benefits, but still use the same existing Java API that you're already familiar with using when connecting to AWS. And our use cases extend beyond just TLS and connections over the internet. For applications that need to use cryptography in their application, such as for client-side encryption, you can use the Amazon Credo Crypto Provider, which again is a Java library that provides the same standard Java interface for cryptography that you might already be using in your application, but is powered by AWS-LC and gets all of the optimizations and security benefits of using our implementations of those algorithms. Here is some more information. what I'd like to call out as interesting is the link to the Amazon Science paper, Verified Cryptographic Code for Everyone. There you can learn more about our formal verification improvements in AWS-LC and the work we did with Galois to verify the algorithms. My coworkers also just published a blog post tomorrow preparing today for a post-quantum cryptographic future that goes into more depth on the recent NIST announcements and how AWS-LC is adopting post-quantum cryptography. And if you're really passionate about post-quantum cryptography, we have some reInvent talks that cover that and more talks on FIPS in the cloud. Thank you. You can reach out with any questions to antop@amazon.com, and I'll be hanging around next to the stage for any questions or anything you'd like to discuss about cryptography. And please complete the session survey. Thanks for your time.